Good. Great. Thank you for the presentation. Really well done. As you already started my presentation, so I wanted to explain some of this, so it's already clean, so making it easier. I'm going to present, as Andrea said, the work I'm doing inside the Marie Curie. This is a work that has already started in KTH, so it is mostly already 1 year that I've been working in this project, and I still have 2 years ahead. As you can say, it is called harmonic modeling in microtonality. So I was working in this team, that Musicology team. It was because the project already finished, but it's a small team, medium-sized team inside the TMH in KTH, which is a broader group of language and speech and hearing. And the director is Bob Storm, who is the one in the top left in the graph. And then we have some postdocs, PhDs, and also a postdoc that is behind. You can see it here. I don't see it here. And then the first part of the project was, as Andrea said, I was working in modeling Western pop music, like in symbolic music notation using the transformer. And through the process, I started conversations with Bob and colleagues, also with Ken de Kernel, which I am working in collaboration in this project, and doing some sort of informal conversations and philosophical questions about what is a chord, how could we define the position of the chord in a kind of latent space to help a transformer recognize better information about the quality of the dissonance or consonance sound of the chord. And so from this perspective, we arrive into this idea that there might be another chords that are not well explored in the corpus of the music, at least in the Western perspective of music theory. And in giving a little of the context, you might remember this paper from 2012 from Joan Serra, measuring the evolution of contemporary Western popular music. Something interesting about this paper is that it shows that a strong evidence of stagnation in ways of, in general terms, in ways of that pop music in Western culture was doing mostly the same recipe in terms of chord progressions in mostly all the songs in the last 50 years, but it's 2012, so we can say 60 years already. We were also conducting research in KTH about differences of AI music and human music. So we gathered more than 2,100 songs from Last.fm, which is related to the 1 million song dataset. But 1 million song dataset is just a short snippet of few seconds. So then we search the name of the song into Last.fm. We downloaded the songs. I can tell you how we downloaded. And then we downloaded also Suno and Udio, more than 2,000. Now we have like 500,000 songs. So you have a lot of files from Suno and Udio. And we compare tendencies of chord progression. So this graph is showing some tendencies in the human music, in pop, that you will see that is a strong tendency into this functional chord that is 4, 5, 1, right? As when you play the fifth chord in the piano, 4 and 1. And also there is a strong evidence of using this canonical 4, 5, 1, or 6. And there is a lot of songs that use this kind. This is a really short list. If you want to see the list and read it really quickly, I say short because the number of songs that use this canonical progression is huge. This is just a quick idea of what I'm talking. So then going into more precise ideas of modeling chord progressions in microtonality, in the literature you can find these Anderson, Thorsen, and Miranda. They developed a framework that was based on a system that is not anymore available, is discontinued. It was called a computational model for rule-based microtonal music theory and composition. And they wanted to propose a system that adapts chords and fuse the location of the notes and to fit into just intonation. That means they want to make the notes to be more aligned with the harmonic series, right? So as you know, harmonic series have some sequence of notes that are overtone. And then you can have the fifth, the octave, the third, and seventh. So this is the first 6 or 7 harmonics, and then you have the small ones. But these first 6 or 7 harmonics defines mostly the just intonation notes that can be used, for example, in this case. But they commit also a little bit a mistake that they didn't really measure the differences of the chords, because they said the system as available triads in major minor diminution method, and this is just from 12th tet. This is so that they are fixed into still in the same framework when they are offering a microtonality. So yeah, that mostly is an error. There is another paper that is really interesting that they go into the psychoacoustical perception of the chords, and they define that 31 tet. 31 means that we divide 31 notes the octave into equal distances. And they said that there are a lot of really interesting chords from this resolution, and they propose that it has to be explored, but there is no quite a specific method of how to explore this, right? So the principle that is used behind all of these project, you can find it in a paper from Adrian Fokker that is 1963, quite a long time. And you see in the graph, we have a perception of the harmonic series roughness. I'm going to explain it a little bit better later. And the idea is that if we divide the octave in 1,200 cents, and if we try to find where is located the perfect fifth in terms of the harmonic series, you will find this irrational number that is 701, 9550, and many infinite other numbers. And that could define the resolution of the division that we want to use, right? So if we look into the table, you will see that now in the Western pop music, we are using, not only pop, Western in general, we are using the ratio 7/12, so that we are dividing the octave in 12 notes, and then we are constructing or building scales of 7 notes inside these 12 options. And we have modes, as you might know if you know some music theory. You can play different modes on it, and then from that framework, all the music theory we know nowadays that is applied not only to Western music, also to bossa nova, to blues, which is not Western. And 7/12 ratio gives you an approximation of the perfect fifth into 700 cents. And if you see the graph, you will see that the perfect location of the perception of the harmonic series are these orange dots, is where the location are. And you see the 12th tet are slightly detuned. So if you listen to a musician like Jacob Collier in an interview saying that the piano is detuned, it's not well tuned, and then he starts singing the correct is more aligned with harmonic series notes, it's actually perceivable by the ear that is singing the in tune note. Okay, there is a lot of also cultural interpretation in this context. So all of this is also shaped by how we practice the music. There is no an absolute truth. It's just how we can explore differences in these ranges, right? Also Nicolas Mercator and Isaac Newton in a non-official paper, this is most as a manuscript. I think Newton was busy with other kind of science, but they described exactly this idea that 31 and 53 ratio was the one that was more precise in terms of the Pythagorean construction, the 12, and then the just intonation. So it fits well. So it is like mostly an intersection. It's a point of intersection. And humans are good perceiving 53 divisions per octave. It's much more precise, but when you practice, it's possible to get it. So farther than this, I think we go beyond the possibilities of the ear to describe the differences in these microtones, right? But we can find 53 that also in Makam, in other cultures, and some musicians develop a total perfect ability to play with it. And there is also a paper that explained that, for example, in Turkey, in the music schools, the range of students that have perfect pitch is really higher than the European ones. And the hypothesis is that actually 53-TET help them when they are kids to be more precise into the differences. So they develop. Of course, this hypothesis is not proved, but the difference is evident. So yeah, so it could open some other research. So the main point that we have here when we talk about 12-TET, 31-TET, and 53-TET, as you know already, 31 and 53 are related. Is that 31-TET have subminor, minor, neutral, major, and supermajor intervals, qualities. So if you think about chords and you want to play with thirds and sevenths, for example, in a tetrad, if you have 5 options, then you have 25 options. Some of them are not new because you have minor and major, but some others sounds a little bit different. So this is the foundation of the project mostly. And in 53-TET, we have 10 different small intervals into these ones. So it opens up much more alternatives. So part of the problem statement here is when modeling chord progressions in microtonality, is the absence of formalized microtonal harmonic theory. There is no defined vocabulary into the chords that can be shaped in this resolution. Also, the digital audio workstations like Ableton Live, they give you the option to play with 53-TET, but that means you have a piano, MIDI piano in 128 notes. It's a full range of the MIDI piano. So if you divide in 53, then you have only 2 octaves and a little bit more. So then you reduce the whole entire range into one simple chord. And this is exactly the graph I have here. This is a major chord, and then you are over. You don't have much options to move around. So it's limited. So this project already resolved that part because it's just a technicity using a MIDI polyphonic expression. If I have time, I can explain it better. And there is a gap between microtonal principles in terms of chord formation and practical composition. There is a lot of new musicians working with microtonality, as said, Jacob Collier, Madame Ashman, and Maddie Ashman, sorry, Mark Cognilio. But some of them have the approach to this from the perspective of 12-TET, which is normal. Then they find the piano in instruments like Lumaton. Lumaton is this instrument that you have keys for 53-TET or 31. And then they start moving around, finding other options. So that means the exploration is still intuitive and there is no framework to do exploration of this kind of vocabularies. So the questions that are behind the project is like in Western modern music theory and some non-Western pop music are based on 12-tone equal temperament triad relationship, forming chords with interval equality such as minor and major thirds. And then one of the questions we realized when I was working in KTH is what defines the quality of a chord. This is a really simple question, but it's actually an interesting question because that opens many perspectives on what you are going to do to then teach, for example, a transformer, right? What is really a chord? How to extend these harmonic possibilities using other tonal equal temperaments, or let's say other resolutions, more precise resolutions. What kind of chord qualities exist? Chord quality means if it's major, minor, dominant, subdominant, or something new, right? How to model chord trajectories in that resolution is also interesting because we have some principles from the 12-TET, but it can be defined in a specific method. How to develop a computer application to navigate that information and provide musicians with these kind of tools so that musicians are going to have an option to navigate harmony, not from static systems. So if you use Ableton Live, if you like Ableton Live, and you use chord modeling applications, then you have some chord that you can drag, and then it's still a mystery. It's just based on, and I like it, I don't like it, right? So to resolve the first question, I would like to explain this principle that is mostly coming from the William Setter's book, which is a really nice book that is called Tuning, Timbre, Spectrum, Scale, it has new versions. The new version is 2005, but actually it was released in 1998. And then you have this dissonance curve, that is the relation of two notes in terms of the distance between these two notes and how the ear perceives the dissonance of these two notes. So when you imagine you have a fundamental in any pitch, it could be, for example, A or 220, and then you start moving another note up in a band, yeah, until the octave. And then you measure how the ear is perceiving the connection between these two sinusoidal frequencies. Of course, we are talking about simple sound, simple sinusoidal, or maybe a triangle. If we use complex timbrical, like a bell, the graph is totally different, right? So it's dependent on how stable are the notes. And this is the graph we have. So, but then you will see that, for example, the octave is very consonant. It is perceived mostly as the same tone. It's just the double. But in between, we have these other points that you can find the most consonant locations. And when you have notes that are really close, the roughness, the beatness, that it creates this beaten sensation. So it goes on more dissonant. So, for example, when you are closer, you have this moment that is the higher dissonance perception. So this is only one axis. Imagine that this is one axis and it describes only two notes. But if we have three notes, we are going to have something like this. That is a matrix with three notes. When you have the root is going to define the location of the matrix, and the other two notes are going to be this comparison matrix as we have here in the plot in the graph. But you can also create a three-dimensional topology. And if we look into this three-dimensional topology, you will find that it has local minimas inside, where the location of the most consonant spots into this triad. And inside, if you look carefully, you will find where are the standard thirds, like major, minor, augmented, and diminished thirds, or triads, used in 12th. So you will see that they are not exactly in the most consonant, but close. Oh, sorry. That opens some questions, actually. So how do the 31th and 53th triads fit on this topological dissonance perception map? They are going to be placed in other locations, and how many of these triads do we have? Then how to form a 4D reference plot. Why 4D? Because then we will be able to see the tetrads, the seven chords, right? Like dominant, minor, minor, minor seven, major seventh. One question is if this 4D topological map is applicable to identify qualities of the seven chords. And this is interesting, and it's something that actually we want to test with Andrea. We want to see if it's possible to use this topological map to enhance the capacity of a system to recognize exactly what chord is being played, because we can reduce any chord from any audio into this tetrad and then place it as a latent space. And then if we put it into a 4D, we have a plot like this. That is imagine that you have a 4D representation when you have the root, you have the third, the fifth, and the seventh, and the root defines this map. So this is actually eigenspace because every spot is a vector that is having a direction into the most consonant location inside. Then what you are seeing here is a visualization as a cut. Imagine you have a 4D cheese and then you cut it, and you have this 3D, right? This is the perception of the plot in space. And this is interesting because then it's a visualization of a map of perceiving tetrads in a specific space. And you will see that, of course, red are the most dissonant locations, and the blue ones, and also inside the blue ones, are going to be placed the chords in a specific location. So this is the principle that is being used in this application. So the application is now developed using a web application. I was doing it before in C++, but in C++ is very versatile, but it's difficult to then deliver the application to musicians. They will need to install things, to try different systems. Yeah, it has some caveats. So now it's being developed on a web system. I'm going to show you the web. And the principle is that you are going to have this wheel that is divided in 53 tabs, and inside you will have the 12 notes and also the 7 notes normally used in the scales, in modes. And it's possible to edit and create. I'm going to show you how they sound. And then you can experiment on the different colors of different modes, also played with the MIDI piano, and then play with new modes, because this mode doesn't have names yet. So it's part of the project to then propose a new naming based on the ones already exist, and then show other options of, for example, in modal interchange. So modal interchange is this idea that you all know what is a mode, right? So you have the Ionian, Dorian, Phrygian, Lydian, Mixolydian. But depending, mostly if you have the white keys in the piano, and if you play from C, you have the Ionian, that sounds a major, so you have a happy birthday song, right? And if you go to the D, if you move to the next note, you have the Dorian mode. So this is what you see here is just a transposition into C. So then you have two alterations in the scale. You have a minor third, a minor 7. And if you continue doing the same, you will have like additional alterations into the modes. But the idea when you have a modal interchange is that you can have a progression, some chords that are based on a functional harmony in a root, and you can then borrow the same structure from other modes. And this is a standard composition like tool that musicians that knows modes and know scales and know principles of harmony use to compose music. So Aaron Parks is a perfect example that he likes to play, for example, Phrygian substitutions into his harmony, so it sounds interesting. But the idea of the application is going to show you this immediately, that you don't need to learn by memory everything, right? So it's give you like a foundation where you can navigate these kind of ideas. So I can show a demo right now. We will try to make it sound good. I don't know if it's going to work. No, I have to. Okay, so this is the complicated part. When I'm going to show the audio, and while showing the course, I will try not to speak. So it's going to be like this. So this is the eigenspace, as I said before. In this web, you can navigate the eigenspace. The idea is that you can zoom it, you can look around. I can move this maybe. I cannot take it away. You don't see it there, but I see it here. Oh yeah, there. Okay, so here we have the eigenspace, and as you can see, if I zoom in, I position chords inside. I don't. I ask a computer to position this inside. So the idea is that it's possible to, for example, if I center this, here we have the chords, and it's possible to see the vectors directions into this space, right? So it's also possible to click any of these notes. So if we go, for example, to the dissonance ones, and if I click, and so on. So let me zoom a little bit into what we have here, and I can try to explain it. As you can see inside the eigenspace, we have, I'm going to clean for a moment the notes. I'm going to clean these chords. I'm going to show only the 12th. So here you will see located the major chord, the minor, the diminished, the dominant. So we can listen to them. I can also change the pitch of the root in the keyboard from the standard 12th from using just the keys. As you can see, it's changing the location of the root. So I can experiment finding different ones. I can also change the double the note that is inside. So just to play with voicing, I can show you. Sorry. Then that means we find 12 dead chords inside this eigenspace. We can also measure the distances between the local minima. All of these white spots are the local minima, so they supposedly sound good. We can test. The local minima, I'm going to organize them also from the most stable to the less stable, because they also have a scale. And if you listen carefully, they sound obviously familiar, but if you try to find these chords in the piano, you are not going to find them because they are fixed, right? The notes. And the visualization in the left is actually showing you how it is fixed. So if you see the line is not exactly in the note, it's shifted. So it's giving you the real location. So this is actually a spectrum visualization, right? It's just the notes of the piano is just to have a reference. And if we listen to the 31 tet chords, they sound like this. For example, this one I just played is supposed to be a dominant, which is an unstable chord in 12th tet, but in 31 it's stable because it fits into the harmonic series. So it doesn't have this unstable feeling anymore. So it has it could be used as a standard way of a blues chord that can go into a resolution, but it can be also used as a fundamental because it's really strong as a block of sound. So it opens options for music understanding of how these relate. And if we go to 53 tet, then we have many other options. I can play some. Some of the ones are called neutral. Neutral means that the third is in the location of the just intonation, and then we have the range to the minors and to the majors. So we have a palette, you can say a palette. This is majors, and I can go to the middle. So this is even more minor than the 12th tet minor. So if you have ever heard someone saying that minor is sad and major is happy, then we have a lot of sad chords here, even sadder than the 12th tet. Of course, that's absurd. It doesn't exist. It's just a joke, right? And the idea is that if you have here then a chord grid, and the idea is that you can, for example, place here a chord, save it. I'm going to play. That means I can use this core memory as my reference of my experimentation to what chords I am using. Also, I can change the pitch, so to change where is the root of the chord. And the idea is that Ableton Live is going to be used as a reference in the timeline to trigger this, so you can start composing with your own system in Ableton Live and this reference. And this is from the Econspace reference, and then you can go to the Model Studio that you can play with the wheel I showed you before. So I can show you right now. This is the standard 12th depth, as you can recognize. And we can start, for example, moving a little bit the location of the in tune and try to listen to the differences in the perception of the sound. Which one is more in tune? Difficult to know. I will say this one is more in tune than the piano. 12, sorry. And so that opens options for compositions. We can go to the modal interchange, and as I said, you have the standard 1, 4, 6, 5. So this is a chord progression, pop chord progression. And then what is happening is that it forms the modal interchange options by default, automatically. So it is Dorian, then Phrygian, then Aeolian, and then relative, also Dorian, Phrygian, and so on. So of course you have to tell me which one you prefer. Or we can do other trajectories just randomly. Yeah, there is no rule. It's just like suggestion. So we can clean this, and the idea is that this map, this core memory that is being organized in the Eigenspace, is going to be also available in the Model Studio. So if you click, it's going to automatically set the disposition in the feature automatically, so you don't have to start dragging all the time. And the idea is to save this into a text file that you can keep in your computer and just drag it in, so you can save your setups or share it with others. So this is what I have right now. I can show you just the last thing. So for example, here, if you have a chord in the grid, you can also edit the voicing in the voicing there. Yeah, and destroy the chord if you're in a bad mood. That sounds quite accurate. Yeah. So yeah, this is the project. I think I showed you already the background and how is the situation with the development of the tool. Something important. You have MIDI here, so you can choose to connect to Ableton Live. So this is the connection. You also have the information here in how to do it, and also technical information about the project. And then in Ableton Live, I can go to Ableton Live here. Where is it done? And I have here the receiving the web as a MIDI controller. So I can start composing in Ableton Live with these resolutions already. So let's test it. So let me just show you what can be done. Let me open the audio for the Zoom is already there. I can do experiments like an arpeggiator if you want to do science fiction things, music, whatever, right? So it's not sound. Yeah, I'm going to turn it out. So sorry. This is the end of the presentation. It's already 49. Oh, you almost. Yeah, I try to run. I try to run because of the delay. So the idea is that I'm going to share this web is already online. It's this link you see here. I'm going to post it into the MTG Slack, and if you are interested and you are not in MTG, you can write me. And we are going to start composing songs. And the idea is to start making a collection of experimentations without any rule. You can do whatever you want. Of course, I'm going to do science fiction, gaming, music, because you already heard I am going that direction. But I have some other colleagues that are doing perhaps heavy metal, like my friend Ken de Garnel in Lille. And so yeah. And this is part of the project. It's not only about training LLM, it's more about music, the process of what can we do with AI to foster not the product, but the process, as Anna Jordan might say, right? So yeah, thank you. This is all. Questions?
Thanks a lot, David.
We managed to finish in time.
Yeah. Thanks a lot. A very great presentation. Questions online. As usual, you can raise your virtual hand, or here in person, you can raise your another. Anyone?
Yes,
please.
Thanks a lot. That was great. Yeah, it looks very inspiring, the work. It would be great to play with this. So I'm gonna ask you for the link. Unless, yeah, I just find it on in the Slack. I think maybe I didn't understand a part, or I just got lost there, or it was not fully explained. This dissonance maps, the dissonance cube and the dissonance topology and so on. How is it measured exactly? Because you say it measures how dissonant chord is in the ear. This I think what you said more or less.
Yeah.
Yeah. What is the method? And because you must have you are doing this, right?
Yeah.
In order to be able to construct these maps, or do you get these maps from somewhere?
Good question. This is the most scientific question, I guess, because it's exactly the part that can be tackled. The criticism of the project from the scientific view. So it's a fantastic question. Yeah, I'm not measuring at all.
Okay.
This is explained in this William Setter's book, and it is called a clumped level dissonance curve.
Okay.
The first version of the paper, they did it with some subjects that they have a kind of questionnaire with sinusoidal frequencies and showing different location of two notes. And if I don't remember, the questionnaire was first by hand, and then they started to do a perception test. I don't know exactly how they were recording, or how was the mechanism of recording the perception of the ear. But this is the old version, because William Setters was inspired on that dissonance map, but he did it by a formula. It's just the formula mostly of how you perceive the harmonic series.
Okay.
So in the book, it is explained the formula and how it is done. Actually the book is online. If you go to the web.
But so it's like some kind of heuristic. So it's like they measured like the perceived dissonance, and then they just basically fit some kind of equation to.
Yes.
Yeah. Okay.
Exactly.
I see.
What happened? So if you go here to the info,
Okay.
I have the link of the book.
Oh, cool.
And I just took exactly the same formula of the dissonance map.
Okay.
Yeah.
Yeah.
And this book is actually really nice. It's really nice. William Setter's book. You might know it well.
The tuning timbre spectrum.
Yeah.
Okay. Okay. Yeah.
Yes.
Okay.
So, of course, these curves can be changed. There is no rule. Actually, this map I am showing is more as a conceptual representation of a latent space. It's just an exercise. It is not the truth about perception, right? And also there is a cultural component on how you perceive these kind of things.
Sure.
We cannot say this is the model. But at least it's useful to start as all of this idea actually came from the part of the project that I was not explaining. And we have also a master's student, Harmonic, that we are working in the idea to model like symbolic music notation translated to MIDI, and from the MIDI train a transformer, but in the positional embedding of the transformer give this positional eigenspace, and then teach the model exactly where are located in this imaginary space, because it's an imaginary space. It's not your ear space. It's just an imaginary space. The curves, I think we can change them, but I don't see it's going to be a huge difference in terms that they are harmonic series. And as long as we can test the software and agree this is dissonant and this is this consonant,
Sure.
we can move forward, right? The problem would be that if I say, oh, this sounds so dissonant, and you perceive it like a beautiful chord, in a totally rejection. Yeah, of course, it's so precise that the map is really useful in as it is right now. Yeah. So maybe if there is a new curve of the perception of the harmonic series and relational to note, then I will have to adapt.
Yeah.
Yeah.
But then you could just change the formula and that's it.
Yeah, exactly. So I am not doing any experiment.
Yeah.
I am not testing anything. Yeah. So I think to be careful in this kind of argumentation, I have to say that this space is actually an imaginary.
Yeah. But when you refer to the latent space, you're actually talking about this space that is not exactly, because, well, maybe my kind of connotation with latent space would be like there is some like latent model involved that is like
exactly.
statistical model, let's say.
Yes.
But it's not necessarily. So yeah, we're talking about like encoding based on this like dissonance cube, not like machine learning direct encoding.
So no, the machine learning, the positional embedding is going to be based on this.
Yeah, but that's like a separate kind of project.
No, it's the same project. It's just I am just starting.
Yeah. Okay.
Yes. I will have that.
Okay.
Yeah.
But so if I can continue.
Yes.
Because you talk about like where you are at the moment, but maybe you didn't talk like so much about like where is it going actually, or like I would be curious to hear, because like I understand that this is like how you're gonna represent the chords.
Yes.
But like, what's the goal apart from like exploring this like newly available space? Let's say.
Yeah.
You want to train like transformers.
Yes.
To say like what for are they?
Exactly. So this is the next step. So to train a transformer, also induce synthetic data, because if we have MIDI with 12 depth and we have local minima points and we can measure the distances between of the nodes with the local, we can do some sort of attractor. We can fake the data and then try different methods. So if we train, so we have two options. We can train only using the current vocabulary because we have the data from the iReal book application, iReal Pro. I use it for a previous transformer project, when I was in KTH. So that is going to mostly learn the probabilities of these chord progressions in different styles. Then we can ask this model for the chord progression instead of doing by hand as I was doing. So it can give you like an idea of, if you say I'm going to start with this chord and I want the bridge, so it's going to give you the bridge options. Then you have automatic modality to change from that. So that means the suggestion has amplifies into other trajectories. But then you can ask or you can adapt the model that is proposed in the first step with the fit, because you already have a wheel with the setup.
Yeah. So the idea is like to train it on the Western music.
Yes.
In 12th.
Yes.
But then in this in this 53 that with the dissonance cube, so like it can kind of generalize and then sort of just apply the same rules, but to another point. Let's say.
And you yourself derate.
Yeah.
Yes.
Okay. Yeah.
The other option is to create a database first by inducing the derail computationally with an algorithm. I don't have idea which one, but there are some. Depending on the techniques, we can find the candidates neighborhood. We can do some sort of classification or clustering, random. So you can try different methods, invent the data, and then train, and then compare which model is more interesting.
Yeah.
This is part of the project, but the main goal of the project is to provide tools for compositional experimentation. Yeah. So the AI branch is not the main branch, right? So AI is not the ultimate solution. And actually, is trying to avoid that the AI is going to tell you what to do.
Yeah. So just like a tool in the tool set, basically, or it's like a part of one of the tools.
It's a tool.
Yeah.
It's a tool for musicians to compose.
Yeah.
And that's actually the key factor that was explained in the Marie Curie. Yes. So that was the most important aspect. That is a tool for musicians to foster the practice. Yeah.
Cool. Yeah. Very cool.
Any other question?
I have a question, like a very small one about like the interface you have in the last interface you showed. On the bottom right, there was like a spiral shape thing that you would use to kind of edit the voices. Like, could you explain like why this spiral shape?
Okay, yeah, good question. The spiral is not fully my idea. Okay. As it is a collaboration with this colleague from Lille, Ken Cornell, we were thinking what is the best method to visualize the voicing into a constrained space. And we found this paper from I know the name, I just have to think. Chuen. It's like CHEW. Chu. Yes, exactly. So he has this final representation of chords, but of course he's using it with perspective. He's showing it like going like this. So this is the same from the zenithal view. So you have the root in the center, and then the spiral goes from the center. So that means the ring that are more closer to the center are the low frequencies, and then you cannot edit the root because the root is mostly coming from this wheel.
Yeah.
Right. I didn't show that you also have inversion in the chords. So you can make super interesting chords if you want. and then the root is fixed, but then the next notes you can move any. And if you break the chord, of course the system doesn't have anything to name it. So then it's just broken. I think I am editing, let's say this one. If I start breaking the construction of a chord, then it says only C because it doesn't have anything in the database to recognize the color. But if you go into the system that it recognizes the 7 and the third, it's going to automatically say that this is a minor sub major minor 7. And so it's already giving information about how it is formed, the chords. So you see, for example, this one is up minor 7.
Right.
Yeah. So this idea is already in a paper explaining. And what he wants to explain the two paper is the relationship between different chords, because then it was showing some sort of tonets in a 3D space. There is a lot of research on showing trajectories of chords. From one branch is tonets, other branch is more complex spaces. This is also idea of the project is to find way to visualize these connections. It has a little problem that then we go into visualizing a 4D. So then it is not quite intuitive, the trajectories. So I don't know if it is a big addition, but yeah, we will see if it happens. Yeah, this is coming from that paper.
And a follow-up question on the chord labels you use, because here I see like in this grid that like this type of notation is for the 53 set.
I can show you. So here, for example, in this plot, you see that we have namings, right? So that means if you go for a sub minor third, and then you go to sub minor seventh, it just blended. So you have a sub minor 7.
Right.
So the system is just recognizing if it's in the range of the thirds and sevenths, and then picking the name that belongs to them. So,
but still, it is not possible to label all possible chords, because you were showing that like the system breaks. I mean, like you were changing.
You can break because the perfect fifth is okay. You also have augmented region and diminished region that will also serve for the naming. It's going to start being a little bit longer, but as long as I break the structure of the chord, so if I go not to the fifth but a sixth, and then I move so I can go beyond these options. Yeah, so it's possible to try to label all. This is also future work.
All right.
Yeah, and I'm trying to use the terminology that is already available in the 53 TED. So I'm not inventing the names by my own. This is just using the convention to show the name. And most of the names are really easy because major is just major, minor is just minor, in the same way to have the that. And then you have this identification that is the up or the down. So that means up major or down major. It's same for minors. So it's not complex. It's easy to understand the chord. So once you, for example, you start playing with the 53 TED and you see a chord, it's going to be really easy for you to know where is the chord in a Lumat or in this system. Right.
Interesting. Thanks a lot. So, do we have any other questions?
Maybe let me see in the group.
Yeah, I think here
people is already gone.
Yeah, some people. I mean, we are almost already over time. So, if there's no further question, I will thank again David for the presentation. Very interesting, very fascinating work, and I think we're looking forward to the next iterations and the future update of your work. So please keep us posted. Maybe
future work is also applying this into automatic estimations. If you have questions, you can tell me.
Thanks a lot. Thanks again.
Bye. Thank you.